Modern finance is moving toward the autonomous junior developer, an AI agent that receives a high-level request and immediately writes the Python code to solve it. Scaling this capability depends on the safety of the execution environment rather than the intelligence of the underlying model. Most systems connect an LLM directly to a Python runtime, creating a direct path to the institution's core data. Large language models operate as probabilistic text generators, predicting likely token sequences, introducing inherent uncertainty. Financial databases, however, are strictly deterministic, operating on rigid mathematical rules that reject variance. When this mismatched AI-generated code interacts with the database, the result is system-wide failure, corrupted ledgers, broken calculation loops, or deleted records. Prompt engineering and fine-tuning attempt to reduce this uncertainty, but they cannot eliminate it. This gap requires a zero-trust financial kernel, a multi-layered architecture designed to treat every AI output as a potential system risk. To achieve zero-fault execution, this kernel integrates rigorous safety protocols from industries where failure is not an option: defense, aerospace, and industrial controls. The first vulnerability is the inference leak, which occurs whenever sensitive portfolio data leaves the internal network to be processed by a cloud API. External processing risks violating data residency laws and exposes proprietary trade secrets to anyone with access to the cloud provider's logs. The military manages this level of sensitivity through CyberNet, maintaining a physical air gap between critical data and the public internet. In this kernel, we apply that air gap by running local weights, like the Gemma model, on an on-premise GPU cluster. Local execution ensures the entire inference loop, from prompt to result, remains contained within the institutional firewall. By air-gapping the hardware, we satisfy data sovereignty requirements and establish the secure physical foundation of the system. Beyond privacy, the system must address semantic hallucination, code that is syntactically correct but mathematically wrong. An AI might confidently generate a Python script that calculates simple interest when the portfolio requirements demand a compound formula. Aerospace engineering solves this through formal verification, where software for systems like the Mars rover is proven mathematically sound before it ever runs. The kernel replicates this by inserting a theorem prover gate using formal specification languages like TLA+. In this workflow, the AI must first output a logical specification, a mathematical blueprint, before it is permitted to generate any executable Python code. A deterministic theorem prover scans that blueprint, checking the logic against financial laws to ensure the calculation is sound. If the proof fails, the process is terminated. No code is written, and no data is at risk. This layer converts correctness from a probabilistic hope into a mathematical certainty. Even verified logic can be used to hide an execution escape, a malicious command designed to exfiltrate data or compromise the host. A Trojan horse command inside the code could attempt to delete system directories or open unauthorized network ports. We neutralize these threats using a two-stage cybersecurity defense: an AST static gate followed by a WASM sandbox. The abstract syntax tree module scans the code structure for forbidden system calls before the script reaches a runtime environment. Code that passes the scan is executed within a WebAssembly, or WASM, runtime. By default, WASM has no access to the host file system or network, creating a hardware-isolated environment for untrusted logic. The combination of static analysis and sandboxing ensures that even malicious code remains fully contained. The final layer of the kernel prevents the resource black hole, the infinite loops or memory-intensive recursions that crash local servers. Standard clock-based timeouts are often too slow and unpredictable to maintain stability in a high-frequency financial environment. Industrial controls solve this with watchdog timers, physical fail-safes that snap a connection if a process exceeds its parameters. We translate this to software through deterministic instruction counting. A modified Python interpreter increments a counter for every single bytecode instruction executed within the sandbox. If the execution exceeds a hard-coded limit, the system triggers an instant kill switch, terminating the process mathematically. This eliminates the best guess of a timeout, providing an absolute guarantee against resource exhaustion. This multi-layered architecture creates a complete end-to-end pipeline for the zero-trust financial kernel. To see it in action, we submit a request to calculate a 10-day value at risk for a live portfolio. The request passes through the local model and generates a rigorous proof in the TLA+ gate. Once verified, The Python code clears the static scan and enters the isolated WASM sandbox. The code runs successfully within its instruction quota, returning the final data to the user. For compliance, every step, the proof, the code, and the results, is automatically logged in an immutable ledger. This new architecture transitions financial MLOps from a reactive culture of monitoring to a culture of mathematical proof. In this system, the model provides the raw logic generation, while the surrounding kernel acts as its physical compiler. By integrating these cross-industry protocols, institutions can finally unlock the velocity of autonomous AI without compromising the absolute security